Hi everyone, and here we go with lesson 3 of Unit 4. And so we're finally going to get into some math again. For some of you, that's a comfort. For some of you, maybe not so much, but that's okay. I think you'll find that this is it's pretty straightforward. Now, this is a bit of a longer lesson in terms of the examples and stuff that we'll do, but again, we'll just kind of work through it gradually, and I'll show you some examples as we go. So what we're trying to establish today is ways of expressing the concentration of a solution. And so we're going to try to do it both qualitatively and quantitatively. And so when I use the term qualitatively, we're going to do it with words. So qualitatively is a quality of, and it's describing using words, and quantitatively it's describing using quantities, or numbers. Okay, so qualitatively and quantitatively. Well, let's start with qualitatively. And so qualitatively, like I said, is how would you describe the concentration of something using words? And I found this diagram, and I thought this diagram was an excellent description of it. And so basically, we're going to use terms like dilute, or concentrated, or words like saturated. Those are qualitative terms. And so look at what we've got here. We've got, here's a test tube with just water in it. And in the first test tube, I've added a little bit of copper sulfate. I can see a spelling mistake there. It should be S-U-L. And anyway, but they've got, so you're going to add copper sulfate, and you can see that the liquid starts turning a light blue color. And then in C, they add a little bit more copper sulfate. It's starting to get darker in color. And then here at D, they've added as much as they can add to where it's saturated, so it's very concentrated at that level. So you can see that in solutions that the more of the solute you add, the more concentrated it becomes. So that term concentrated, if I told you that you had a very concentrated solution, you would know that a lot of solute has been added. If I told you you had a very dilute solution of it, you'd know that not very much of the solute had been added. And a good example of this is orange juice. You can have orange juice from concentrate, and where it's extremely concentrated, it's almost like a syrup. And then as you add water to it, you make it more dilute. You dilute the orange juice, and so it becomes a little bit less. And so dilute and concentrated are these qualitative terms that you can use to describe solutions. Okay. But what we're mainly interested in, I got to be honest with you, is quantitatively. So this is the second way of describing the concentration, and this is by putting a number on it. So we're going to learn 5 different ways of describing the concentration quantitatively. Okay, so these are the 5 methods that we're going to learn. I have to admit that 4 of them are less common. Well, I shouldn't say that. It's less common for chemists. I'm going to say less common in chemistry, but probably actually a lot more common in day-to-day life. And you'll see some examples of that. Less common in chemistry. And then I'm going to put a star beside number 5, because this is the main one that you're going to use moving forward from today. This is the main method for this course. So, if you had to concentrate on one of them, you'd concentrate on that last one, but you'll see all of them. Like you'll see all of them like in your assessments, but definitely it's that last one that you're going to have to use over and over again. So we're trying to describe the concentration of something, like whether it's concentrated or not. We're going to use some formulas. All right, here we go. So the first formula, and I've just given you the formula here. So I'd like you to to know this formula, and basically it's called a mass volume percent, and often it's called an M/V percent. And the way you calculate this is it's the mass of solute in grams divided by the volume of the solution in milliliters. And I'm gonna just put a little tick mark next to those just to remind you that you have to get grams and milliliters, and then you multiply it by 100%. And you typically use this method when it's a solid dissolved into a liquid. All right, well, let's try a question. It says a solution of hydrochloric acid was formed by dissolving, and here we go. I'm going to put some givens here. It was hydrochloric acid was formed by dissolving 1.52 grams of hydrogen chloride gas. Now, interestingly, I just told you it was a solid in a liquid, usually, but here it's a gas into a liquid. That's fine. So here we go. We've been given the mass of the solute. I'm just going to give it a little subscript here. The mass of solute is equal to 1.52 grams. It's dissolved in enough water to make this amount of solution. So we've also been given the volume of solution is equal to 24.1 milliliters. And I notice right away that I have the grams that I need and the milliliters that I need. And they're asking us, what is the concentration in a percent MV? Okay, so required is this M/V, the mass volume percent, is our question mark. Okay, so the analysis, it's basically the formula that's at the top of the page here. And so I'll just write it. It's the mass volume percent is equal to the mass of the solute divided by the volume of solution times 100. Okay, so let's sub and solve. So subbing in, the mass volume percent is equal to 1.52 grams divided by 24.1 milliliters times 100. And when you plug that into your calculator, you get 6.31%. So the mass volume percent is 6.31%. Okay, so there's an example of a mass volume percent question. Okay, the second type of concentration, quantitatively, is a mass percent. So you'll often see it written as an M/M percent or a percent MM. And it's the mass of solute in grams divided by the mass of solution in grams. And it's normally when you combine a solid into another solid. And I wanted to put this little chart in here just to show you that a really good example of this is with alloys. So alloys of metals are combinations of metals. And so you'd often give them as a mass percent. And so a good example is brass, which is made up of copper and zinc. Well, the copper is 85% mass. So 85% of the alloy is copper and 15% of it is zinc. Another example is stainless steel. It's made up of 78% iron, 15% chromium, and 7% nickel. And so you can see different types of examples of alloys. Okay, well, let's try this question. Stainless steel is a variety of steel that resists corrosion. Your cutlery at home can be made of this material. Stainless steel must contain at least 10.5. So over here, I said to you it's 15, but the industry standard is at least 10.5% chromium. So what mass of chromium is needed to make a stainless steel fork with a mass of 60.5 grams? Okay, so here we go. I like this question just because it's just a slightly different approach. So in this case, we've actually been given the mass percent. You don't always have to be given the other parts. So here you've been given the mass percent is 10.5% for the chromium. And it says, I'm just going to write the required. It says what mass of chromium, so I'm going to call that the mass of the solute in this case, is a question mark, which is the chromium, and then is used to make a stainless steel fork. So that must be the mass of the final product, and so that's the mass of the solution is equal to 60.5 grams. So I kind of had this, I was looking up at my equation as I kind of interpreted the question. I knew that I needed those. So in this case, I've been given the mass percent, I've been given the mass of solution, and I'm trying to solve for the mass of the solute. Okay, let's write our equation. The mass percent is equal to the mass, oops, I won't go, I'll just write mass, I'll write it as a little m, of the solute, the mass of the solute divided by the mass of the solution, which is, all of the metals, times 100. Okay, let's sub and solve. So I've been given this 10.5%. I'm trying to solve for the mass of the solute. I've been given that the whole fork, which is the entire, all the metals mixed together, which is the solution, so it's 60.5, and then times 100. Okay, so I got to solve for my unknown there. Well, if I divide the 100 off of both sides, you're left with 0.105 on this side, is the mass of the solute divided by 60.5, and then to get the 60.5 over, we multiply both sides by 60.5, and so our final answer is going to be 60.5 times 0.105, and we get 6.35 grams is the mass of the solute, which is the chromium in this case. Okay, so there it is. So you can be given the mass, the percent, and still solve. Okay, the third type of quantitative measure of concentration is a volume percent, and that's often used when it's a liquid dissolved in a liquid, and it's the volume of solute divided by the volume of solution. All right, let's try this question. 60 milliliters of ethanol, so that's the volume of solute, is equal to 60 milliliters, is diluted with water to find a final volume. So my volume of solution is equal to 400 milliliters. What is the percent percent by volume? So what is the volume percent? And by the way, remember that it could be written like VV percent. Okay, is equal to question mark. One thing I want to mention in this question is sometimes they'll stick a little trick in there, and they'll say, well, 60 milliliters of ethanol is diluted, and they might have said with another 400, or I'll use another number, 320 milliliters of water. Notice that in order to get the volume of the solution, you'd have to add the two together in that situation. In this case, they've given you this final volume, so they've given you the volume of solution. So just remember that in some situations, you may have to add the two together to get the volume of the solution. All right, so here we go. Let's give this one a try. Our volume percent is the volume of the solute, or the one that's there, the one you're interested in, divided by the volume of solution times 100. Okay, so let's sub and solve. So the volume percent is equal to 60 milliliters divided by 400 milliliters times 100. And when you do that, you get 60 divided by 400 times 100 is 15%. Okay, so the percent of ethanol would be around 15% in that case. All right, number 4. So number 4 is something called parts per million or parts per billion. And basically, here are the formulas. For the parts per million, it's the mass of solute divided by the mass of solution times 10 to the 6, basically times a million. Or for parts per billion, it's the mass of the solute divided by the mass of solution times 10 to the 9, which is a billion. So you tend to use this one when the proportion of solute to solvent is very small, but it's still significant. And so what I mean by that is if the substance that you're dealing with is, let's say it's a poison, and even if it's there in trace amounts, it could be deadly. You would be interested in knowing the parts per million or parts per billion, rather than being given a number like 0.000003%. You're going to be given something like, 30 parts per million. Well, again, it turns it into a number that's a little friendlier to work with, but also it's significant. If I was interested in the amount of radioactive waste in a substance, parts per million can be huge and can be deadly, and so we're interested in that number. Okay, let's try one of these. So 17, it says the concentration of chlorine in a swimming pool is generally kept in the range of 1.4 to 4 milligrams per liter. The water in a certain pool has 3 milligrams per liter. Express the value as a parts per million. Okay, so they've given us a hint that 1 liter of water has a mass of approximately 1,000 grams. And the one other thing I'll say is that if you've got 4.0 milligrams, you would have to divide it by 1,000 to get grams, and so it's 0.004 grams. Okay. Oh, I'm sorry. We were actually doing it for this one, so it's let me just fix that up. We were interested in, okay, here we go. So it was 3 that we were interested in, which is 0.003 grams per liter. Okay, so here we go, given. We have been given that we've got this 3 milligrams per liter, which is technically 0.003 grams per 1,000 milliliters, or 0.003 grams per 1,000 grams. And that was just based on that last little hint there. Okay, what they're asking us for is the parts per million. And here's the formula I'm going to use. Let's get rid of this. Okay, the formula I'm going to use is mass. Well, here I'll write parts per million is equal to the mass of the solute divided by the mass of the solution times 10 to the 6th. Okay, so let's sub and solve into that. So parts per million is equal to 0.003 divided by 1,000 times 10 to the 6th. And when you do that, you get 3 parts per million. Okay, so there's an example of using parts per million. Okay, the last one, and this is the one that I said you're going to be using the most. I've written here that it's the most common in chemistry because it relates the number or count of particles to volume. And sure enough, you can see that this is using our little n. And if you think back to the hub, remember that our little n was in the center of the hub, and we could use little m to get to the number of moles. We could use capital N to get to the number of moles. That's the number of particles. That's the mass. And down in this corner of the hub, we can now use concentration and volume to get to the center of the hub. Okay, so you can see that this is going to be very powerful. And so the formula is the concentration in moles per liter, also called the molar concentration, is the amount of solute in moles, or the little n, divided by the volume of solution in liters. Now I'm going to circle the liters here because in the last few we've been using milliliters, whereas in this formula for concentration we use liters. So just be aware of that. You've got to have your answer in, or your inputs in liters. Okay. Well, let's try this. Okay, number 21. A student dissolves, so here I'm going to start writing, a student dissolves 30.46 grams of silver nitrate. Well, hopefully a lot of you will recognize that if you're given grams, that's a little m. So you've been given 30.46 grams of silver nitrate, AgNO3, and it's dissolved in water, and it makes 500 milliliters of solution. So the volume is 500 milliliters, but I remembered that I always needed liters, so I'm going to switch it. So you divide this by 1,000. To go from milliliters to liters, you divide by 1,000, so it's 0.5 liters. And it says, what is the molar concentration? So my capital C is the question mark. Okay, well, my formula is C is equal to N over V. Okay, but I look at that and I go, well, I've got the V that I need, but I don't have an N. Oh, but I've been given a little m, and so I know another formula. I'm going to write it over here. N is equal to little m over big M. All right, I think I'm ready to go because I can see that this is a two-step problem. I'm first going to have to find the little n, the number of moles, and it's 30.46 grams divided by, and now's where you're going to have to go to your margin or the bottom of your page. You're going to have to find the molar mass of AgNO3. You guys are experts in this now. And so you turn to your periodic table and you figure it all out. I've already done it. So I get 169.88 grams per mole. Okay. So I write that in here, 169.88 grams per mole. So now I can calculate the number of moles. So I divide those two, and I get 0.1793 moles. Okay, now I go back to my original equation, and I go concentration is N, 0.1793, divided by the volume. So this, remember, is in moles. This 0.5, I got to get it into liters. And so I divide those two, and I get 0.359 moles per liter. There we go. And we are done. That's the concentration. That's the molar concentration, or the moles per liter. So there we go, you guys. There are 5 different methods of finding concentration, quantitatively finding it. Obviously, the higher the number, the more concentrated it is, The lower the number, the more dilute it is. And those were the qualitative ways. So I've put some homework questions here. I've indicated which ones I'd like you to do. So it's a couple of each of them, a couple of each type. And the answers are on the back here. So good luck with those. Take care, you guys.